Hello everybody and welcome to this video in our series about graph data science. In this video we're going to learn about centrality algorithms, which are one of the traditional categories of graph algorithm. So centrality algorithms are used to try and work out what are the important nodes in their graph, and there are lots of different ways of determining importance. It could be that it's based on the number of connections, as in degree centrality, or perhaps it's just which node is the most easily reachable within a graph or subgraph. Or perhaps what we're interested in is finding which node has the most control over flow in a graph. Or perhaps it's the transitive importance of a node that's important to us. So let's go through those one by one. So degree centrality, I think this is probably the simplest of the algorithms. And the idea here is that we're counting the number of incoming or outgoing relationships from a node, and we're using it to find popular nodes in a graph. And so that could be used to find something like which is the most popular Twitter user. So maybe we find out Katy Perry's got 45 million followers, and that would be a way of using degree centrality to work out who are the important users on the Twitter social graph. Or perhaps it's used for detecting fraudsters from legitimate users in an online auction site. So perhaps they're doing way more transactions than a normal user would. The next one is closeness centrality. Now here it's a way of detecting nodes that are able to spread information efficiently through a subgraph. And let's just quickly have a look at the formula that's used to compute this. So what we're working out is we want to know what are the number of hops from each node to every other node in the graph, and then we're going to sum those up and then we'll divide it by 1. And so what we get is what we call the average farness of a node, where a farness of 1 would mean that you can reach every node with 1 hop. So there's a direct link from you to every node, and then a lower number would mean that you're much further away. So the higher numbers are better here. And this algorithm can be used to help maybe detect individuals in favorable positions to control and acquire information in an organization, or it could be used to maybe as a heuristic for estimating arrival time in a package delivery network. Between the centrality is the next one we're going to look at. And again, here we're looking at it's a way of detecting the amount of influence that a node has over the flow of information in a graph. And it's sometimes useful for finding out which are bridge nodes, which ones are sitting on the intersection of lots of different subgraphs. If we took our Twitter example again, maybe there's a community of people talking about Java and a community of people talking about Neo4j, and we're trying to find out what's the person sitting on that intersection. And again, there's a formula that we can use to compute this. And so what we're saying here is that we want to work out for every pair of nodes in the complete case, for each pair of nodes, find out how many shortest paths there are between those nodes, and then find out how many times each node, a specific node, fits on that path. So we're trying to see, for a particular node, how many times are you sitting on the shortest path between other pairs of nodes in the graph. Now, between the centrality, the complete version is generally takes very, very long to run, because it's got to compute the shortest path between all pairs of nodes in the whole graph, which doesn't really scale to big graphs, and so you'll usually use an approximate solution here. And again, it's useful for finding influences, and they're not necessarily the people that are sitting in management positions. It can also be useful for finding the transfer points in a network, such as an electrical grid, or perhaps for microblogs to figure out how can they spread their blog around Twitter into other subgraphs. And then the last one that we're going to look at is called PageRank, and this one slightly different to the others, and this time we're trying to find the transitive influence. We don't just want to know our influence on our own. We want to know are we connected to other important nodes. And so this one originates from the Google search engine, and it can be used for recommendations. So Twitter have a variant of this called personalized PageRank for one of their recommendation systems, or it can be is often used in anomaly and fraud detection systems. And there are a couple of variants of this algorithm as well. So I guess you could consider actually PageRank as a variant of eigenvector centrality, where we're interested in the direction of the relationships. And then there's another variant called article rank, which is similar but is quite a bit better suited to some use cases. So that's the end of this video on centrality algorithms, and hopefully you've now got a better understanding of how to find the important nodes in a graph.